Good evening, everyone. Thanks for joining us for our stargazing lecture for it's February, for the month of February. I'm Dr. Cameron Hummels. I am a research scientist here, and I will be your host for this evening's event. No, you don't need to applaud for me. Thank you. So these events, just a quick layout of our schedule for tonight. I'm going to have a few brief announcements for a couple minutes. I'm going to talk about the upcoming solar eclipse and how you can best appreciate that if you are so inclined. And then we'll get started with our presentation, which is going to last about 30 minutes or so. While the presentation is going on, we have a couple of astronomers outside setting up telescopes. You may have noticed that there was some haze, some cloud. It's not ideal observing conditions. However, we're going to give it a shot. As long as we can see the moon and Jupiter, then we're good to go. So we have a couple telescopes pointed at those right now. And so after our speaker's presentation is over, you can either go outside and look through the telescopes. You can stick around in here. We're going to have a Q&A panel consisting of the speaker, myself, and two other members of the department, taking questions from all of you on whatever questions you have about astronomy or space science or physics. And we'll go until the end of the night around 9:45, 10 o'clock. And so you're free to go back and forth between, asking us questions or going outside and looking at the craters on the surface of the moon or Jupiter or whatever you wish. For reference, this is being recorded. We're live streaming to YouTube Live right now. So if you watch this and you want to see that really interesting moment that you forgot what happened, but it'll be recorded. You can go on our Caltech Astro YouTube channel and find the recording of this lecture along with something on the order of 100 other lectures from the past several years on a variety of different topics. So feel free to check that out if you're interested. Our next event, these events happen once a month here in this room. Our next one will be March 15th, Friday, March 15th. At the same time, being given by a professor in the department named Jamie Bach, who is the principal investigator of a new NASA mission that's being launched later this year called SphereX. It's going to do all kinds of really cool stuff in terms of mapping out the sky in parts of the infrared part of the spectrum and calculating the locations and the light that's coming from different, like something on the order of a few 100 million galaxies across the sky. And that's going to provide insight into a variety of different parts of physics and astronomy and cosmology, but notably it's going to provide some insight into the early expansionary period known as inflation, when the universe was exponentially expanding and growing larger over time. So it should be very interesting, and you're hearing it from the horse's mouth, the principal investigator, the main person behind this mission that's going to launch, which should be really cool. In addition to these events, we have events that take place in Old Town, Pasadena once a month on Monday nights called Astronomy on Tap, which, as the name suggests, take place at a bar or a restaurant. These ones take place at what's called the Dog House, which is like an outdoor beer garden / hamburger joint in Old Town. It's a few miles from here. And for those, we have a couple of informal 20-minute science presentations along with astronomy-themed pub trivia and telescopes and such. They're really fun. Our next one is in a week and a half on Monday, February 26th, and it will feature a PhD student in the planetary science department talking about the different composition of different objects, planets and planetesimals in our solar system. So like ices and rocks, and how they're similar and how they're different. And we'll also be featuring a presentation by kind of a renowned science cartoonist named Zach Weinersmith, who writes for a webcomic known as Saturday Morning Breakfast Cereal, which is pretty hilarious in my opinion. And he's not talking about the webcomic though. He and his wife just put out a book that's all about the science and ethics and law surrounding if we can actually settle other planets in space, like space settlements. Because oftentimes you'll hear about space settlements from Elon Musk saying colonize Mars, or Jeff Bezos, and you have to take it with a grain of salt, right? Because these people they probably truly do want to do this, but they certainly have something to earn if we go full bore and land on these planets and have space settlements, since they're the ones who have the rocket production that will get us there. So the whole point of this book is kind of to dispel some of the myths about and take a real skeptical view of, is it realistic for us to send people to settle on the moon or to settle on Mars or to colonize the rest of the solar system, or is this kind of a pipe dream, or is this going to happen in our lifetime or not? So anyway, he's going to be talking about that book, and I think his presentation's actually going to be on the case law surrounding space cannibalism, because there's actually a bunch of law surrounding that, because there's law surrounding maritime cannibalism. So it should be interesting, but there will be copies of the book that you can buy and he'll sign and such. So that should be cool if you're interested. And then I'm sorry to hold you up here. And then one last thing I wanted to talk about is this upcoming eclipse. At the door, you may have gotten a pair of Eclipse glasses, Caltech Eclipse glasses. These aren't just for the eclipse. You can wear them. I mean, you could wear them right now. You won't be able to see very much. You'll look really cool though. So these eclipse glasses block out the bulk of the light coming from any sources. That's why they look dark, but it's safe to look at the sun with these eclipse glasses because they're blocking so much of the light that's coming to us. And so if you go out tomorrow and it's a clear day and put these on and look at the sun, you'll only be able to see the sun in the sky, but you'll be able to see, a distant kind of yellow orangish circle in the sky, and that is the light coming from the sun, and it is safe to look at the sun. Now, it is much more interesting to look at the sun when it's undergoing an eclipse of some sort, because you'll see the moon passing in front of the sun. And it turns out that such an event is right around the corner. On Monday, April 8th, there will be an eclipse passing over all of North America. If you happen to live in a kind of 100-mile wide and 2,000-mile long path, you'll be in the path of totality, or the center line, where the moon will totally cover up the sun for a brief few minutes. And so that path, I should have put out a map here, but I'm going to put together a presentation on this and put it on our YouTube channel in the next week. So stay tuned. It'll be like 15 minutes and give you the details on this. But essentially that path will go, it enters in through kind of Western Mexico and then travels through North America, up through Texas, through the Midwest, and then cuts over at New England and exits out kind of New England, Canada. And if you are along that path on Monday, April 8th, sometime around noonish, depending on your time zone, then you will be one of the lucky, tens of thousands where when you look up in the sky, the moon will pass over the sun and it'll get dark for 4 minutes around noon, which is really a crazy experience, partially because it gets dark, but partially because of all the other things that happen. The wildlife doesn't know any better, so they think it's nighttime, and so crickets start chirping and birds start cooing, and it actually drops in temperature a little bit depending on where you are, because you're in shade now, and when previously you weren't. And when you look up where the sun was, instead of seeing the sun, you'll see this black circle on the sky with kind of this glow around it. We'll hear more about that glow over the course of tonight's presentation, the solar corona. And it really is a special experience. So if you have the opportunity to go to one of the places where this will occur, it's, in my opinion, it's worth it. Because you hear about all kinds of astronomical things that you should go to, like the supermoon. The supermoon's not all that super, but this is really super. This is really cool. Aurora Borealis, the northern lights, super cool. This is really cool. Meteor showers are pretty cool. So yeah. For those unable to or unwilling to travel, it will be possible to see the eclipse from other places all across North America, but you won't get this same experience where it gets dark. From here in California, you'll get a 50% partial eclipse, which is where the moon passes over about 50% of the sun, and you won't be able to notice really with your naked eye, but if you put on these babies, you'll see a crescent sun when you look up at the sun. Don't look at the sun without protection like this, because you could really damage your eyes. Yeah, so we ourselves are going to be doing an event here that morning. Here the partial begins at about 10 a.m. and finishes at about 12:30 or so. The peak will be at about 11:15. I think we're going to have a lecture in here during that time. I mean, I realize people have to work and they can't just it's Monday, free day, go see the eclipse. But if you want to, or you are free, we'll have viewing on the adjacent athletic fields. We'll be handing out eclipse glasses. We'll have solar telescopes. It'll be pretty sweet. So definitely think about coming out. And for those of you who are traveling, we're going to be doing events in along the center line in a community known as Piedras Negras in Mexico, right across the Texas-Mexico border, where totality will last about 4.5 minutes. You'll have about 4.5 minutes where it gets dark out during the middle of the day. So yeah, we're setting up public education events in that community and partnering with one of the institutes there, the universities there to do these cool events. So, but there's nothing special about, I mean, I'd like to think there's something special about our event, but there's anywhere along that path of totality will be awesome if you can get there. Okay, thank you for listening to my many announcements. So our speaker for tonight is going to talk more about the sun and this kind of mysterious solar corona that you can see. Up until recently, you could only see during a solar eclipse. And he's going to tell us about that and what we can now learn from a space telescope that's passing close to the sun itself. So our speaker originally hails from just around the corner. He grew up in Monrovia, California, just down the block, and Highland Park, before he went on to his undergraduate studies at UC Santa Cruz in Northern California. And then he went far afield to do his PhD in Wales, where he went to, oh goodness, Aberystwyth University in Wales in the UK, and did his PhD in physics there before finishing just a little over a year ago. And now he is back in the area, and he is a postdoctoral researcher here doing some really interesting work on this very subject here at Caltech. So I'd like you to all welcome Dr. Gabe Muro. Forgive me.
Hi, so my name is Gabriel Muro, as Cameron mentioned, and I'm going to talk about how we are, oh no, I touched something, how we are chasing the solar atmosphere in a variety of different ways, specifically with total solar eclipses and, as he mentioned, Parker's solar probe. So this is the 2017 eclipse. That was my very first total solar eclipse, but I got to see a few more after that, and I was able to do some science of the next couple of ones. So let's just start really simply with what the sun is before we really get into the solar atmosphere and all this stuff. So the sun is basically far away, 150 million kilometers away, and it's around 98 million miles away for us Americans. It's around 100 times wider than the Earth, so it is pretty large, very, very large, and its mass is a little over 300,000 times the mass of the Earth. As you probably have noticed, it is very, very, very bright. Now, the composition of the sun is well known to a certain extent. We know that it's roughly made out of things like hydrogen and helium and all that other stuff, which we, our bodies are made of, our, technology is made of. All those other things are basically all clumped into just a category that astronomers like to call metals. So things like carbon and oxygen are metals as well. And the temperature, at least the temperature that we are probably most familiar with at the surface of the sun, is around 6,000 Celsius or 11,000 Fahrenheit at the surface. So it's pretty hot at the surface. That's not comfortable at all to sit around in. But why is it so hot? Where does that heat originate? Well, there is a lot of hydrogen, as I mentioned, and deep in the core of the sun, all of that mass, that 300,000 times the mass of the Earth, is all cramming together at the center and creating extremely high pressure due to gravity and doing something called hydrogen burning. Basically, it's forcing those hydrogen atoms to become helium. Basically, you take 4 hydrogen atoms, you cram them together really hard, and you get a helium atom. But if you were to add up all of the mass of that helium atom and compare it to those original 4 hydrogen atoms, you'll find that a little bit of mass is lost. Basically, it disappears as something called like a gamma ray, which I'll just call energy for simplicity. And Einstein was able to calculate this relationship here. You've got energy equals mass times the speed of light squared. So basically, the sun at its core is converting mass into energy, which means that it's very hot at the center. So much of this mass is producing something like 100 billion hydrogen bombs per second of energy. That's per second. That's really tough to wrap your head around. And that creates a core temperature of much hotter. 15 million degrees Celsius at the center. That's a big number. I haven't even converted that to Fahrenheit yet, but trust me, it's very, very, very big. Much, much hotter at the core than it is 6,000 degrees at the surface there. So where does that heat go? Well, we know it eventually gets to the surface, but it's not a simple path there. It radiates outwards through something called the radiation zone. And as the material and heat rises to the surface, it starts to act as what we call a fluid. It's, some people would call it a gas or plasma or even a liquid or something like that, but they're all fluid, and they create this, fluid sort of motion. Oh no, everything broke. Let's see. Creates this fluid motion here and creates churning in what we call the convective zone. So we would call this right here a convective cell, where you have heat rising from down below, rising up to the top, and as it rises to the top, it spreads out, releases a bit of that energy, and now that this material, basically that hydrogen and helium and stuff, is cooled down, they begin to sink over at the edges and creates a convective cell. Now, what we're doing is what's happening on the sun is all of that hydrogen and helium is so hot that their electrons have been stripped, and it creates an electric current and creates also a magnetic field as a result. And this means that the sun, in all of these many convective cells, is producing strong magnetism just below the surface of the sun. And we can see this magnetism reaching outwards. So, is that really so simple? Of course not. No, it's very complicated, which is why I have a job, thankfully. And as you consider not just the convection that's happening here, but also the rotation, you start to notice something very strange happening on the sun. The fluid and material, basically those hydrogen and helium atoms and their their gaseous and plasma form, are moving faster at the equator and slower at the poles. So that means it's basically getting twisted up. If you can imagine just kind of twisting your belt line just a little bit faster than your upper torso or something like that, well, eventually you'd get really twisted up. And these twisted interior magnetic field lines begin to create something called sunspots, which are just really strong magnetic zones. The magnetism in those sunspots is so strong that it actually stops a bit of the fluid flow, which is why we see these dark areas. They're a little bit cooler. They're, nice and chilly, like 4,000 degrees instead of 6,000 degrees. So yeah, that's essentially how we get heat at the center to rise to the top and generate magnetism. And as all of this churning of ionized particles of just protons and electrons and helium with less electrons than usual occurs. So sunspots, as I mentioned, are really cool. And here is a what we call a potential field source surface model that lets us visualize. These aren't lines that we can actually see. This is a computer generated image of basically the magnetic field lines extending out of these sunspot areas. And as you'll notice, many of these magnetic field lines don't really connect back onto the sun. They flow just out into space, and that's how we get particles off the surface of the sun. These particles will tend to follow magnetic field lines, and those that are in what we call closed loops, which just loop from one part of the surface to the other, they tend to stay at the surface of the sun. But the ones, all these pink ones and green ones here, particles will follow along those outwards to us out here, out in space, basically Earth and Parker Solar Probe, which we'll eventually get to. So normally, all that fun stuff is going on, but this is usually what we see when we put on those eclipse glasses. We don't see anything too interesting. At solar minimum, we've got, let's say, just orange sphere. It's cool, but not so interesting. And during the most active periods of the sun, during solar maximum, you've got these little sunspots which are visible, but we can't really see the magnetism at all. We don't know exactly what's happening. We don't know what the effect of that magnetism and all those particles are off the surface of the sun. As you guys remember from this very first slide I showed, we can see the solar atmosphere here. But when we take a look with visible light normally, what do you guys see above the surface of the sun? There's really nothing there. It's a very difficult technical limitation to observe the atmosphere of the sun, which means we have to hope for a very unique situation to occur. Something like a total solar eclipse, which allows us to see the light from the solar atmosphere and learn a bit about what's actually happening above the surface and learn a bit about that magnetism and the particles floating around just above the surface there, the stuff that actually interacts with us here on Earth. So the first spectroscopic investigation of the solar atmosphere was done way back in 1869, where oh gosh, I forget this historical astronomer's name, I apologize, but he discovered a green line dubbed coronium. Now you might be wondering, wait a second, when we take a look at this stuff, it's all just yellow. Where do you get those green lines and red lines and blue lines? Well, we pass light through a prism, and when you do that, you create a rainbow. But when he did this, he found that there was a very strange bright color that appeared. He called it coronium because he didn't quite know what it was. He thought it was a new element, perhaps. But in fact, it ended up being iron, the kind of iron that that our cars are made out of, and then our just pieces of metal and stuff here on Earth are made of. But iron on the sun, because remember, it's very hot. Iron is in a plasma form. Basically, it's hotter than liquid, hotter than gas in a plasma form. So he asked himself, and a few astronomers later on asked themselves, well, exactly how hot do we have to get to make iron into a plasma? And what is this iron 14 here? Well, it means that it's so hot that some of the electrons in that iron atom have been ejected. And we call it iron 14 because 13 of those electrons have been ejected from this particular type of iron. Now, the temperature required to actually do that, the energy input necessary to raise the temperature of an iron atom and get it to eject 13 electrons is somewhere in the area of 2 million degrees Celsius. Now stop for a second. We said the surface of the sun was 6,000 degrees. Typically, and in the center, it's very hot. So typically at the surface, as we're moving away from the center, it cools down 6,000. But then you move a little further away into the solar atmosphere, and suddenly the temperature goes back up again. That's a little bit confusing, which is why astronomers stood very unsure of exactly what was happening until we really started to examine solar eclipses and the magnetism that was occurring in the solar atmosphere. So in 1940, a guy named Edlin, I've totally messed up this slide here. A guy named Edlin identified that it took around 2 million degrees to do that. So today, at least the understanding of why the temperature is so hot is resolved, but what that effect is here on Earth is still much unresolved. So we can measure the solar atmosphere. It's not very easy though. From space, as I mentioned, there are the same camera limitations in space as there are on Earth. We don't really have a camera that's able to visualize the surface of the sun and the atmosphere. It's simply not doable. So basically, we have to wait somewhere between every maybe 1.5 to 2.5 years for a solar eclipse to occur. And we only get around 0 to, if we're really lucky, 7 minutes. The upcoming one in 2024 will give us about 4 minutes. That's not much to work with. You're really crossing your fingers about clouds and weather and everything like that. And to make it even easier for us, it will be at a random location with random weather with Lord knows what else going on. So it's very difficult. We do have spacecraft that are currently launching that may give us the opportunity to visualize those heavy iron atoms and stuff like that in the atmosphere. Or sorry, I'm pretending like this is the sun. But in the atmosphere. But for right now, the best we can do is hope for total solar eclipses to be able to see the sun's atmosphere in visible light. So what I did back in 2020 was I gathered some of my fellow grad students over at Aberystwyth University. We hopped in a plane, clearly during COVID time. This took a lot of government involvement, but thankfully they were with us. And we traveled here, somewhere along the line in Patagonia, Argentina. Now, what's in this case here is a device that I call a spectrometer. And basically that just takes that white light and breaks it into component colors. So it's essentially a very advanced prism that separates that light out, and it measures in great detail that green iron line there at 2 million degrees, but also a couple of other lines. This one here, this orangish line, is iron 12. And that's around 1.5 million degrees to create that. And iron 10 here, which is we're somewhere around 900,000 degrees Celsius, which is nice and cool. So what we did was we went to Argentina. We had planned to work here at this really beautiful original site. It was secluded. We didn't have any disturbances from anybody else. It was beautiful, calm winds. We had electricity to plug into and allowed us to set up overnight. Everything was great until we actually got there and realized that this particular site got a lot of rain and clouds every day, which caused us to throw away all of our plans, toss our equipment in the trunk of a car, and start watching the weather every single day and trying to figure out, well, there seems to be standing waves that form in these clouds. Where do the clouds form last? Who knows? So amateur meteorology, as I call it, became our way of life. And we hit the road at 5 in the morning, and we drove out here to our new site. I can't even really tell you where it is. It's somewhere in the Neuquén province of Argentina. My big question was, are we trespassing? Probably. We had 50-mile-per-hour dust storms, and I had contact lenses on there, so I could only see out of one eye, and we had to set up in 1 hour. And you'll notice in the background, oh no, there's clouds over there, and behind us also there's clouds. There's clouds all around us, but we managed to set up essentially right here off the 40 highway somewhere in Neuquén, Argentina. And crossed our fingers and hoped that the clouds didn't form before the sun was eclipsed by the moon. And so from space on eclipse day, you'll see our site right here in this little patch of clouds at the bottom, and you can see the moon's shadow cross right over, and then shortly afterwards get completely covered by clouds. So we got extremely lucky, and whoa, oh gosh. Like I said, there were really, really loud wind. Let's see. Okay, hopefully this doesn't make the noise. But my device, so let's see, here's our site there. You can see the clouds zooming over very, very, very fast. And what my device was able to capture along this line where I broke up the component colors was the atmosphere of the sun. And we were able to measure it in great, great detail for these three specific lines, colors, which corresponded to very, very hot iron at 900,000, 1.6, and 2 million degrees Celsius. So that worked out really, really well. And I was very, very, very happy about this. And as you can see, just down here, somewhere along the line, that's me. And I bump into my telescope right at the end, and it actually just kind of falls over a bit. But that happened 8 seconds after the eclipse was over, so it's all perfect timing. So yeah, this was really, really, really interesting. So what did I see in that green line? Well, I saw two different portions of the sun. The left side of the sun, there wasn't too much going on. There wasn't anything super interesting going on other than just measuring the temperature. But the right side of the sun, in this case, right along that line, which separated those colors, I was able to measure iron 14. And when I tried to notice how that line was broadened, in spectra we call this broadening. When you have too many particles kind of bouncing into each other, they spread out the line and kind of smear it a little bit. Once I did some analysis, spectral analysis, I found that actually this particular portion of the sun right here was something like 10 million degrees. Really, really, really hot. So even hotter than the formation temperature necessary to create that iron. Also, that iron is moving around, and we find basically through a bunch of different motions, turbulence and Doppler motion, that it required around 10 million degrees for our analysis to make sense. And so why was it so hot? Well, because that particular spot right there was the base of a solar flare and a coronal mass ejection that occurred just before the eclipse. And you can actually see this in the white light here, which is, if you guys want to travel to Texas or Mexico later this year, that's what you'll see. You'll see something very similar to this, maybe not in that great detail, but you can see here this weird shape. And this is only 2 minutes of pictures here, and you can see it expanding rapidly. Essentially, that's a solar storm, or coronal mass ejection, if you're more familiar with the terms. And so flares and coronal mass ejections are magnetic reconnection events. Essentially, remember we talked about all those magnetic field lines? Well, they loop over each other, and they eventually will snap and release tons and tons of energy, converting magnetic energy into heat energy, which is why we suspect the temperature got up to 10 million degrees, at least temporarily. There we go, big solar flare there. And that solar flare was able to generate this movie should play. Here we go. Creates a coronal mass ejection, which you can see is very clearly a bunch of particles being ejected off the surface of the sun. And they are accelerated ionized particles. These are kind of dangerous particles that you don't want to interact with very much on a daily basis. Basically, if you let too many of these particles hit your cell phone, well, your cell phone's going to conk out on you very, very quickly. Or the things that we're concerned with here on Earth is letting your astronauts or perhaps your satellites get hit by too many of these particles, and then they will conk out pretty quickly, which is not great. So how does this actually affect us at the Earth? Well, those magnetic field lines and all those particles eventually will reach the Earth. So this is a simulation of the Earth and the Earth's magnetic fields, and you'll see these big straight lines here, and that's actually the sun's magnetic field. And let's see. And when we play this movie here, it is playing, we can see that this coronal mass ejection shock actually changes the shape of the Earth's magnetic field, not to mention creating relative intensities within this magnetic field, which is full of things like plasma and free electrons. It creates shocks within the solar wind. And unfortunately, we don't really have any way of predicting these things until they happen. Basically, we see them happen at the surface of the sun, and we hope that we basically we hope that we're able to respond quickly enough. So that was in I guess the movie played too fast. That was in, I believe, 2016 or so. But back in 1859, a very, very, very large coronal mass ejection hit the Earth and created a ton of damage. Basically things like, telegrams. Yeah, telegrams and things like that. They actually caught fire. It wasn't such a big deal in 1859, but basically our transformers and power lines catching fire today would be a big, big issue for our civilization as it is right now. So damage to the electrical grid is a major, major issue with regards to the solar atmosphere and whenever it decides to act up. So we can use ultraviolet cameras to provide some information about the surface of the sun. If you take a look at the bottom right, you'll see a pretty large flare and coronal mass ejection occurring, basically material erupting, and you see this warm, very hot area down on the lower right. But that's all we really know. We don't really know what happens beyond that. Is this going to affect the Earth? Is this going to do anything to us? Is this pointing off in the wrong direction? Well, they don't tell us anything about the particles. Basically, what we see doesn't tell us much about what we're actually going to get here at Earth or elsewhere in the solar system, which is why we use Parker Solar Probe along with other what we call remote sensing telescopes to observe and monitor the sun. Really, we're monitoring it and making sure that it's not going to be hazardous on this particular day. So ultraviolet light images are really nice. They create really beautiful images like this. We can see the coronal loops and magnetic field lines a bit, and they monitor from a very safe distance away. They have other things like particle detectors and magnetometers, but Parker Solar Probe is a special spacecraft. It is not trying to stay a safe distance away. It is trying to get as close as possible to the sun with its particle detectors and magnetometers. It doesn't have a camera because if it pointed a camera at the sun at the distance that it will get to, that camera would just melt immediately and probably not just melt, but vaporize and become plasma and part of the solar wind later on. So while many spacecraft have things like big solar panels here to give them energy. Parker Solar Probe doesn't have that. Parker Solar Probe just has a heat shield at the front to protect it from the sun, because getting as close as it will to the sun is very, very, very hazardous. So when we look at the energetic particle detector, when I first looked at this thing, I said, oh no, this sounds like a bad idea studying this. But this is the telescope that we are using. It has 80 different apertures, which will measure particles of different energies, and we're able to figure out the difference between hydrogen and helium and iron and all sorts of different elements impacting this device, and allow us to estimate what sort of where these particles originated from, and how fast they have traveled, and how long it took to actually reach the Parker Solar Probe. So our little device is this tiny little thing behind the heat shield. And this one in particular right here is called our HET, which is our high energy particle detector. We also have the LET, which is the low energy, but really it's the medium level, very high stuff. And then we have another, this one would be called EPI-low, which is still much more energetic than anything in the solar wind. So basically we're just measuring three levels of very, very, very high energy stuff. And so this is a brief video and animation of Parker Solar Probe and how it actually travels close to the sun, and it will reach something called the alphanic critical surface. Basically, that's a whole different talk altogether. But basically, the boundary where the solar atmosphere actually is. Not the solar wind, but the solar atmosphere. So Parker Solar Probe is zooming in very, very, very close, and we're able to measure those magnetic field lines and measure the particles in great, great detail. So this video goes on for quite a while there, but it's really cool. Nice animation from APL. So how close will Parker Solar Probe get? Well, when you actually go and take a look at a total solar eclipse, you probably won't be able to resolve it with your camera, but Parker Solar Probe will be around here, only around 5 solar diameters away from the surface of the sun. So that's pretty darn close. And that allows us to measure the energized particles before they're impacted by the Earth's atmosphere, by the Earth's magnetic field and other things in the solar system, basically interacting with other particles. So we're able to kind of measure the source of these. And that's what we're doing. So here's Parker traveling very close to the sun as one of these coronal mass ejections passes. Let's see. You'll know it when you see it. So you can see the background stars traveling. It does have a camera. It's just pointed at the side. It can't point at the sun. And here we go. We're starting to get close. You'll notice that the animation of the sun is getting bigger. The speed is starting to get pretty... Actually, it's slowing down now. But the distance here was decreasing down to around 11 solar radii, or around 5.5 solar diameters there. And here we can see one of those coronal mass ejections right there. Cool stuff. So the main thing that our device on this spacecraft is measuring are solar energetic particle events. And these are the highest of the high energy particles that are ejected from the sun during these events. We think they are heated up and accelerated by flare energy. Other people, some in the room, some upstairs definitely, will argue that it's accelerated primarily by the coronal mass ejection shock, but we're really unsure. And those solar energized particles are what actually creates the aurora borealis, and also things like polar, I guess, radio blackouts. Essentially will ionize the Earth's upper atmosphere, and we won't be able to get radio signals and stuff across the poles. So this is what we're concerned with. And here's one of these, I guess, parcels of solar energized particles. Now, how many of these does Parker actually measure? So this is the sun here, right where my laser pointer is pointing, up on the top left of the screen. And this is Parker's path. And each one of these kind of red spots are energized particle events, not just flares, not just coronal mass ejections, but energized particle events that it measures. We've only gotten a couple really close in, but I'm going to look at one in particular here. This is the one that occurred right here on the bottom right. I showed a video of that earlier. And what we measured was several different things from Parker Solar Probe, but we have a strong type oh gosh, I always mix this up. Type 2, well, and type 3 radio signal there. The magnetic field doesn't really do anything, but you'll notice as time progresses from left to right. So this is time on at the start of the event, and then later on, we do see suddenly very high amounts of protons blast our spacecraft. In all three measurements here, you can see that over time, the highest energy particles sort of decrease, the medium particles take over, and eventually we get this shock wave from the CME there. So how long did it take for those energized particles to actually reach Parker? Well, it's a little bit alarming when you do this. We do something called velocity dispersion analysis, and basically we take our measurement there, we invert it, and we assume that all of the protons started at the same time and traveled the same distance to reach the spacecraft. And we found that at 0.65 AU, so about 2/3 of the way from the Earth to the Sun, those particles traveled a little bit longer. Basically, they didn't follow a straight line. But when you calculate the speed, it's really, really fast. It's 10% the speed of light. Those are much, much faster than any of these coronal mass ejections. So even when we see stuff happening on the surface of the sun, these solar energized particles come and hit the Earth and Parker Solar Probe before we really see anything moving towards us. So they're not really dense enough for any of our telescopes to actually measure them. Only particle detectors are able to do this. So finally, what I've done here is made a comparison of the elements that we measured at the spacecraft in 3 different locations. So we've got Parker here at 2/3 of the way towards the sun. And then we've got a couple of other spacecraft known as Stereo and ACE, similar particle detector devices. And I've mapped out here many different types of hydrogen, helium, I believe these are the oxygens and iron elements there. And while they do look pretty similar, we find that actually somewhere between Parker and these spacecraft very close to the Earth, we lose a lot of that iron. So we're kind of underestimating how much iron was originally located in these solar vents, and we're really it's kind of mucking up our understanding of when we should be concerned about these solar storm events and whether they're going to affect us or not. So yeah, the big question here is, where did these particles come from? So my understanding, my understanding of it is that we have, and maybe I'll use this one. That's why I couldn't figure out where to put that video. Here we go. Is that we have a small amount of material coming out here on the bottom right, and you'll see that this is a 2-part event. Essentially, we have what's called a prominence, basically material just floating above the surface of the sun, but in a 2-part event. So a small amount of material bumps above what will become a M5 flare, and that is what causes the majority of those particles to move outwards. Now, eventually, when we analyze the what we call ionic composition, we can get back to the beginning and figure out what temperatures were necessary and whether the particles that we actually measure here at Earth came from this little patch of material, or perhaps came from some other patch of material further out in the solar system. And currently, I wish I had an answer for you. My boss definitely wishes I had an answer like last week, but I will soon, and we should be able to characterize at least something about where those particles that actually impacted Parker Solar Probe came from. So I believe that's all I've got for today. So basically, the takeaway is that Eclipse spectroscopy can allow us to remotely observe the atmosphere. So it's a good option, not just for repeating the same thing, but also trying new stuff. So this type of telescope, spectroscopy telescope that I built, was a new design, and I thought it was a really nice idea to have it very portable and able to work in difficult environments. So it's a nice way to test out new types of observations. And Parker Solar Probe measures the atmosphere in situ, what we call it, basically just directly getting hit by these particles. And we're learning a lot about how CMEs and SCPs accelerate away and where those particles come from. So we're refining solar physics theory with unique data and a very unique spacecraft, unlike any other. And additionally, one last thing, which I guess Cameron will probably reiterate, is don't forget that we have a total solar eclipse soon. I've been to 4 of these so far, and they've all been a little bit different, and they've all been awesome. I'm still really, really stoked to be going to the one in 2024, where I'll be making more spectroscopic observations as well. So plan your trip very soon, and this probably will be the end of NASA's big heliophysics year, which includes well, the annular eclipse that we had last October, along with the total solar eclipse, and Parker getting even closer to the sun, and hopefully measuring a whole lot of energized particle events. So that's it. Thanks very much. And if you're wondering where the path is, that's it.
We can take some questions from the audience. I'll get to this gentleman.
Oh, hi. By the way, I think Norman Lockyer and Jules Jansen were both looking at the spectrum in 1869. Question is, you measured 10 million kelvins, and I imagine you'd expect even higher ionization states on the ion. Does the fact that does the fact that you're still seeing iron 14 tell you something about electron densities or something like that?
Sorry, that's a couple of things there. So yeah, that particular event, when I looked at it in the remote sensing cameras and the ultraviolet cameras, it really didn't seem to be much of a flare. So it was quite surprising that that the temperatures had risen so high. That seemed to be mostly due to, I guess, what you would call Doppler motion, basically those particles shifting around and reorienting themselves. The energy needed to reach that amount of motion is equivalent to 10 million degrees of added energy. That doesn't necessarily mean that those particles are at 10 million degrees. So this is really a problem of nomenclature, but it means that the energy deposited in that area is was much higher than we expected for those particular particles there. And sorry, what was the other portion about electrons or something? No, was that it? Okay, all right, cool.
Additional questions?
So you said that CMEs can reach like up to 10% of the speed of light coming out
the solar energized particles. The CMEs, they go pretty fast. They'll go up to like 10,000 kilometers per second, but these at the highest, that's the very highest CMEs. Okay. But the solar energized particles have historically, not during this current cycle, been known to get nearly up to half the 50% the speed of light. So that's like, I don't know, 150,000 kilometers per second. Yeah, thanks very much.
So in theory, if they were going to impact electronics on Earth, you only have like 15 minutes to do something about it.
Remember, there's a delay from the sun. So there's an 8-minute delay from the light, just the speed of light traveling, and those particles are coming at half the speed of light. So that means we'd have like 4 minutes essentially to prepare ourselves, which is not quite enough. And thankfully, at least when it comes to the solar energized particles, those aren't necessarily the things that will set things on fire here on Earth, but they will irradiate astronauts and stuff like that. So that's why I'm not so keen on being an astronaut. 4 minutes isn't much time.
Oh, yeah. Can you pass this?
I'm supposing that the quantum computers and stuff are going to do. I'm just feeling very vulnerable that someday there's going to be this big flash and then everything's going to explode in the infrastructure here, unless, you know, the new computers are so ahead of it that yeah, there must be a huge
there's
on that right now.
There's lots of work going into predictive models. At this point, we haven't gotten there yet. There's a lot of machine learning methods, and I'm sure we're very close to a new horizon of AI models that are hopefully able to predict and basically make space weather less of a concern. But as of right now, we're not there yet. So hopefully in the near future, I'll be telling you about when the next solar flare will come and exactly what the next solar eclipse will look like. But for the moment right now, we really can't predict that. But yeah, I'm pretty hopeful of that as well. So anything else? Or?
Okay. Yeah. One last question and then we'll break.
In the thing right here, it says that there's something called a wolf. There's like a Wolf-Rayet, and it says that it like takes off that it ejects the outer layers of gas and then like has the core. Why does it do that? Like what causes it to do that, and what like effects does it have?
This is, yeah, that's a bit out of my realm. I study the sun, but thankfully we have some.
We'll address this
astronomical
during our
Yeah.
Q&A panel.
Yeah.
These stars, these Wolf-Rayet stars, are different enough from our own sun
Yeah.
that they have some different behavior. But we will talk about it in just a few minutes. So first of all, let's thank our speaker again. Excellent presentation, Gabe. And so now is the choose your own adventure part of the night. We have telescopes set up outside looking at the moon and Jupiter. We're going to set up our Q&A panel in here and answer this question that the young lady had about Wolf-Rayet stars and whatever other questions you may have or our YouTube audience has. One thing I forgot to mention in the announcements, there's an upcoming Dark Sky Festival that we're helping put on in Death Valley in 2 weeks. 2 weeks. March 1st through the 3rd. It's free. It's in Death Valley. There will be telescopes. There will be lectures like the one we just heard, but on many different topics about landing on the moon or water on the moon or different locations in our solar system or space exploration or whatever. We're going to bring up a group of 2.5 like 15 or so people from the department to help out with events up there and science demos. And we're going to host 2 astronomy on taps in Death Valley National Park, which is going to be awesome. So think about coming. But anyway, now's our chance to break. We'll start our Q&A panel in like 5 minutes, and we'll go for about an hour, and the telescopes will go at the same time. If you want to check out the telescopes, go out the front door and follow the lit signs behind us onto the fields just behind us. I'm in the path of totality. Gabe, we're going to get started. Okay, we're going to get started with our Q&A panel. Thank you guys for sticking around. Oh, that's really low. All right. Am I visible in it? When I said I'm visible? Okay, that's fine. I should be decapitated, yeah. Thanks for everybody for sticking around. We're going to get started with our Q&A panel. I'm Cameron Hummels. I'm a research scientist here. I work primarily, each person will give an introduction to who they are and what sort of science they work on, just so you have an idea of our specialties. I work primarily on galaxy evolution, understanding how galaxies like our own Milky Way form and change over very long periods of time in the sky. It takes much longer for a galaxy to change than it does, for instance, our solar system to change or the surface of our Earth to change. And so I try and model that through big supercomputing simulations, how galaxies change and look earlier in their evolution or what their future will be, that sort of thing. So.
Hello, my name is Ivy and I am a grad student here, and I have been working with Greg Hallinan on developing the visible light as well as the radio instrumentation in order to study magnetic activity around stars. So sort of like what Gabe was showing today, those flares, those coronal mass ejections, those solar energetic particle events, I'm looking for those events on other stars outside of our solar system.
My name is Robin, and I work on cosmology. So mostly it's like through like theoretical modeling calculation and using galaxy and cosmic microwave background, trying to study dark energy, gravity, and also early universe.
Okay. Hi, I'm Gabriel. Most of you guys have just heard from me. I am a solar physicist, and I study the sun in a variety of ways using spectroscopy to examine the component ions that we can see, basically the elements that we can see, and also using particle detection techniques to understand those particles that actually reach the Earth, where they came from, and what sort of hazard they may cause to us here on the Earth.
Okay, so now it's your guys' turn. What questions do you have? It sounded like the question about the Wolf-Rayet stars was, yeah, she already took off. But do you have any questions that we can try and address? No question is too simple. Well, there may be some that are too hard, but we'll see.
I have a question for Gabe. During the presentation, you mentioned some stuff about like sunspots. Mm-hmm. So I was wondering if you could explain more about how they form and why they're like lower temperatures.
Okay, so sunspots are those areas of really, really, really strong magnetism, and most of the elements on the sun are what we call ionized, meaning that they have a magnetic charge. It's very similar to just a little bar magnet that you may have played with, where you've got a positive end and a negative end. So these elements will have, like protons will be positively charged and electrons will be negatively charged, and things like helium can also be positive or negative, just depending on how many electrons are present within a single atom. So those sunspots are areas where the magnetic field of the sun is very, very, very strong, so strong that it actually causes those particles to just stop moving for a short period of time. Basically, they are, I don't like to use the word frozen on the sun, but they are stuck in place, I think is a better way of saying it. And as they just sit there, stuck in place, they are able to cool down. They're not churning, they're not new atoms from deep, they're just sitting there and they're able to cool down. Because as you may have seen from the videos, everything in the sun is moving around, but as soon as you stop something from moving, it gets a moment to cool down and stay in place. And so that's why they cool typically to around 2,000 degrees cooler than the other average temperature around it. So does that clear it up for you? Cool. Mm-hmm.
Questions? Yeah.
You mentioned the Parker telescope. Like, how close can a satellite be before like it get damaged? Like, how does it able to read it without getting damaged from the flare or the heat of the sun itself?
Well, okay. Well, any telescope or any device can be damaged even at the distance of the Earth. So those are two separate things. Getting hit by these charged particles in the wrong way can really destroy these devices at any distance. But the difference between Parker and other telescopes is that it has a big heat shield, which is basically just burning off as it gets closer, every time it gets close to the sun. Now, when it comes to other telescopes, we'd have to figure out the average, I guess, equilibrium temperature of, like, let's say a planet. So I know that at Mercury's distance, which is around half of the distance from the Earth to the sun, I believe it's, oh gosh, what is it, 400 Celsius? Oh gosh, okay. Yeah, so these guys don't look at the solar system. I think it's around 400 degrees Celsius. To melt metal, basically the things that spacecraft are made of, we need to get up to somewhere in the area of 800. That won't melt it down into molten metal, but it's enough where we'll start damaging components in an irreparable way. And so just thinking about the scaling there, I think around 1/3 of the distance between the Earth and the sun is about as close as we can get using traditional telescopes, essentially. If you get more than one or less than 1/3 closer to the sun, you're in that danger zone above, I guess, somewhere in the area of 800 degrees or so, where basically your solar panels will start melting, your electronics will start melting, your antennas definitely won't last very long. And so that's really the key factor. So most of the other spacecraft, and I'm thinking historically, I think most of them get around 30% of that distance, which is very close to 1/3. And they don't really delve any deeper than that except for Parker Solar Probe. That's the only one that's able to get there. So yeah. Does that answer? Okay, thanks.
All right.
This question is for Robin. Can you talk about your research in the dark matter or dark energy? And it sounds like you're doing some simulation about it, is it right?
So I personally do not do simulations. It's mostly there's so in theory it's like at a really large scale, like you actually don't need simulation. You can do a perturbation theory. So it's like you have some matter fluctuation over like the density field, and then like the fluctuation is actually captured pretty well by perturbation theory. But once you go to a slightly smaller scale, so here, I mean smaller scale, I mean like several galaxy clusters, like that's what I mean by small. So it's still really, really big scale, but in cosmologists, we call it small scale. So it's like, we refer to like, something is like, it's basically really large in a common sense, but we think it's small. But in that sense, when you try to study those scales, you do need like extensive simulation. So like there's something called n-body simulation. So you can extract how particle evolve under gravity. And so yes, part of like the group, some people, they do need like simulation to get some of the results, especially for like a lot of dark matter study. They actually focus on like galaxy scale. I think Cameron can answer.
Yeah.
Let me add I guess on top of it.
Yeah. So these simulations that are primarily done for computers on studying dark matter they can be on very large scales. Right. So, but yeah, let's normalize things. The size scales of galaxies are kiloparsecs. So let's see. So the virial radius is 2 kiloparsecs. So it's like on the order of 1 million light years across. Big structures. What he's talking about, galaxy clusters are groups of thousands or tens of thousands of galaxies themselves. So a factor of 10 times even bigger than that. So we're talking like 10 million light years across. The computer simulations that we do are, on par with that scale. Where we're dealing with really, really, really big scales, because it turns out that's the scale on which dark matter clusters. Dark matter, while we believe that there's dark matter passing through you and me right now, little tiny little particles that are flying around, they're not clumping on those scales. They clump on the scales of galaxies and nothing even smaller than that. Not planet scales, not star scales, just very large scales. And so primarily the computer simulations that we do these are on big scales.
Yeah, but depending on different scale, right? You can get like different like accuracy or like different treatment. So if like you're only like trying to do a galaxy or maybe several galaxy cluster, you can kind of fine tune like, what's really going on. But then for the scale we talk about, it's like even maybe like, it's like, I think maybe order of magnitude larger on top of that, then like you need to do like many like simple treatments, like you model something simply and then like, so it will mostly be just like simple effect gravity, and then you can treat other effects more like simply, because you simply can't afford to run like large simulation with great detail. So there's a balance between like the amount of detail you can get versus the volume you need to do. So it's just a trade-off between that.
Yeah. There were a bunch of questions from our YouTube audience, so I wanted to ask a couple of those. Many of them are related to the content of tonight's presentation. One was a question from Jie Yuan. Any advice on how an amateur astronomer might take a spectrum photograph of the corona, like the one taken by Miroslav Druckmuller? Or I mean, you were showing some of these, your instrument showing some of these spectra and whatnot of the corona. Is it possible that an amateur could do that with their camera and maybe a simplified setup?
Yeah, I mean, in a very simple setup, you can probably get, well, there's two ways. One is get a diffraction grating. Diffraction, just DIFFRACTION, grating. Basically a little slide, essentially, of that. And I would try to place that in front of your like phone or something and just see what it looks like. I imagine you'd be able to see the component colors during just regular sunlight. Point your phone, not your eyeballs, at the sun. And also, I suppose you could try just feeding one of those, oh gosh, what are the name of those little things where you have a small hole?
Pinhole camera.
Pinhole camera. There you go. Yeah, great audience. A pinhole camera through a prism. So if you just have a regular prism, you can aim that little pinhole camera beam at the prism, and I imagine you would see some pretty interesting colors. That's at least what I would think of if I didn't have as good of funding. So, yeah.
Exactly. And if you, even if you can't get a hold of a costly diffraction grating, you could use a compact disc.
Oh no, I mean like cheapo diffraction gratings that you can buy like for probably $5 to $10 on Amazon or something like that. Yeah, maybe they come in glasses sometimes. I remember during like the 4th of July one year, they were giving away these glasses because they created extra color so that the fireworks looked even more spectacular and colorful. But in principle, it should be able to actually see the spectrum of the sun or the spectrum of anything, because that's what they were doing.
Cool. Great. I'll just take one more question here from the online audience. Are the conditions in or near a solar flare sufficiently extreme to support nuclear fission or nuclear fusion processes?
Gosh, that's a tough question. Because you need to know the density of that material.
It seems like the temperature is high enough. But probably, and maybe the pressure is high, but the density needs to be high enough to cram all those atoms, those nuclei close together to actually.
Yeah, I would imagine there is some fusion occurring, but to sustain that over some period of time, no, I don't think so, because basically those atoms are able to freely move along magnetic field lines. So as soon as they get hot, they expand outwards and they tend to fly out of solar flares and spread out essentially, instead of staying compact and fusing together. But I imagine at least momentarily there probably is some, at least a few, probably more than that, hydrogen atoms actually fusing together into helium. But it's probably happening at such a small scale that nobody has measured it so far. But I think in theory, it probably has happened.
Cool. Okay. Other questions? Yeah.
So this is for Ivy. So based on what we know about the sun, do we expect that stars in all different categories, from like blue supergiants to red dwarfs, have similar magnetic behavior and similar ejection and all that? Or is there some like thresholds where it can't happen or more happens?
Yeah, that's a fantastic question. And the crux of a lot of great research that's happening right now. So we know that a lot of stars that are like the sun, so similar temperatures, similar mass and radii, have very similar flare characteristics to the sun and very similar magnetic field characteristics, to the extent that they even have magnetic cycles like the sun has. as you get to lower mass stars, so those really cool, really red stars, we start to see a transition where these stars no longer have the radiative zone, like Gabe mentioned, that the sun has. And this has some interesting implications for the generative mechanisms for the magnetic fields on these stars. And we see these stars flare way more frequently than we see any other star flare. Part of that is an observational bias. It's just easier to see flares, but part of it is also due to the fact that the dynamics of these stars is just different. And then on the whole other side of the spectrum, for stars that are much more massive than the sun, you have a convective core rather than a radiative core, and a radiative envelope rather than a convective envelope. So these stars tend to not have very strong magnetic fields. They tend to not have very strong flares. There are some exceptions, but generally stars more than like 1.5 times the mass of the sun, you don't see a lot of strong flares from them.
Okay, more questions.
Thanks. So not going to be too scared of Beetlejuice then, thank you. I have a simple question about the 4 minutes that we have of the eclipse coming up. What would be like your dream? Is there a dream amount of time you wish there was an eclipse? Like, oh, for an hour or 5 days, or, you know, is there a wonderful amount?
Well, I mean, we have spacecraft monitoring the sun 24 hours a day in certain wavelengths of light. The problem is that, like I said, there are camera limitations. We have a dynamic, what we call a dynamic range in brightness from the surface of the sun to the solar atmosphere of, oh gosh, I think it's somewhere in the air of like 100,000 to 1 million times dimmer for the solar atmosphere than the solar surface. So my perfect situation would be to place a telescope, I guess, essentially at the oh gosh, I'm forgetting my Lagrange points. The one behind the Earth.
Oh, behind?
Yeah.
In the shade of the Earth?
In the shade.
L2.
Yeah, L2. Place a telescope at L2, or maybe a little bit further than that, and just use the Earth, or probably the moon, to be constantly eclipsing the sun. That's really a tough sell. An easier thing to do would be to take two spacecraft, fly one in front of the other, and basically use that one on, let's say, maybe a 1 kilometer in front of it to block the sun's light, and that way we can see very, very close to the solar surface, but not actually visualize the solar surface, and create a constant solar eclipse with 2 spacecraft that we can observe from the
infinite solar eclipse.
Yeah. That's the big difference between me and the rest of these people at the table is that it's right there. Like it's down there right now, but somebody's looking at it on the other side of the Earth, and 24-hour coverage, not just 24-hour coverage, but like every 6 seconds would be fantastic, so that we can really understand the mechanics in just horrifying detail, essentially. But yeah. Yeah. I'm really hoping that one of these proposals goes through. Well, you have scattering over the edge. So basically, if you put your hand up and kind of block any bit of light, you'll notice that the edge of your hand kind of lights up a bit, and that's due to scattering. So there's a certain distance away, and it varies depending on how big your object is, but there's a certain distance away where scattering becomes, I would say, negligible. It's still there always in some small proportion, but negligible enough where that bright light from the solar surface is no longer affecting the light that you're measuring. And when it comes to the sun, you want to be at the precise distance where you can get nearly to the edge of the solar disk, but of course not over it, and then not have that scattering be an issue. And I believe for the spacecraft which was proposed and unfortunately was rejected, called Sulis, I believe we were looking at 1 kilometer separation between the two, where scattering effect basically became minimized. And of course, if we made a bigger occulter or smaller occulter, you can change those distances. But for the size that we had, which was I believe something a little bit bigger than a CubeSat, essentially, 1 kilometer was the target distance that we were aiming for.
And just to follow up on that, it's useful to do this with stars other than our own sun. Gabe has been talking about, blocking the light from our own sun so you can see this corona around it. But other astronomers who study planets around distant stars want to do this with the light from that distant star so you can see the structure, not usually the atmosphere because that's too low surface brightness, but planets that are orbiting around that star. And there's a variety of different ways you can do that. One is an optical element called a coronagraph, named because of its background in blocking out the sun's light for the corona, but also star shields, which is exactly what you're discussing, having some sort of distant shield that's blocking the light from that host star, but you're getting the light from the surrounding neighborhood. So maybe a planet that's orbiting around it. And I think that there's one that's going on board the Nancy Grace Roman telescope that's launching, the NASA Roman telescope that's launching in the next year or so, I think. I'm not an exoplanet scientist, but is there an exoplanet scientist in the audience who can correct me or... Yeah, so she was talking about the coronagraph, but I don't know if she mentioned if it was on the Roman telescope or not. But there is. Okay, thank you. So here we have an expert, dark matter expert who also happens to know about coronagraph on the Roman. Yeah. So and the distance at which those are, instead of being a kilometer, is like, I think, thousands of kilometers away to sufficiently block out and get rid of this diffraction and the scattering and such. So anyway, just an add-on there. Okay, more questions. You first, and then I'll get to you.
So you talked about the 1859 event that caused, telegraph wires on the surface to catch fire and things like that. I would imagine that the magnitude of that event, had there been satellites in orbit, would have caused serious damage to them. Mm-hmm. So is there any kind of understanding, and I guess maybe this is a hard question because there's a lot of variable things like direct hit, indirect hit. The atmosphere is not always the same thickness in terms of effect on the ground at different times of year or times of day, even maybe. What is the understanding of like how, if something like that event happened today with the tens of thousands of satellites that are orbiting above the atmosphere without the protection of the atmosphere. What's the duration of the event? In other words, so like satellites that were on the other side of the Earth when it hit might be safe, or is this something that would go on long enough that they would rotate into its path? What is it? What do we think for things on the ground, like 1859? Okay, so well, two things. The 1859 event, which we called the Carrington event, of course, the instrumentation and stuff we had back in 1859 was not exactly, the same as what we have now, but it was estimated to be something in the area of what we call an X31 flare. These days, anything like it's a big number. These days, I believe the largest flare that I recall off the top of my head is an X19. So basically, you're adding quite a lot of zeros in the relative energy out of that. And we're not really sure why we haven't seen other X31 flares occurring on the sun. It's thought that perhaps there might be a completely different mechanism going on that produces these really large-scale events. And until we see one, we don't really have any way of studying it or predicting, if this will happen again. As for the effect of something like that, assuming that it's a regular flare and coronal mass ejection, and we probably had an SEP event during the Carrington event, a typical solar energetic particle event, which is what we're studying, what I was mentioning with Parker Solar Probe, that can continue for several days. That can continue for just in some of the events I've looked at, like something in the area of 10 days of a bombardment. So basically any satellite in orbit would eventually be no longer shielded by the Earth's magnetic field, which during the Carrington event, basically the magnetic field becomes sort of negligible. Basically, the magnetic field, the protective front of it, drops down into the atmosphere, so the atmosphere starts getting ionized particles directly. As for the CME, which is the bulk of the, I guess, lower energy, but still quite hazardous ionized particles, that also can continue for several days. So if we were to try to protect ourselves from this, we would turn off our spacecraft. But you would have some small issues of atmospheric, basically some of the atmosphere would be pushed away from the upper atmosphere, and it's not a lot. It's not enough where we would start losing oxygen or anything like that, but it's enough so that the atmosphere of the Earth becomes shaped a little bit oddly, and we'd get kind of a tail. As satellites would pass through that, this would cause drag on those satellites, which are probably turned off, and they would start to degrade in their orbit. They probably wouldn't crash down, but when we turn them back on, they wouldn't necessarily be where they're supposed to be. I'm not sure how that would affect the GPS satellites, and along with everything else that relies on the GPS satellites, but probably would create issues if they manage to survive. On the ground, the best thing to do is basically just shut off the power grid. Because essentially what happens during these events is that a ground current starts to form, and usually when we plug electrical devices into the wall, there's that little third plug on the bottom that allows excess electricity to go down into the ground. But during one of these events, it would go in the other direction and overwhelm essentially all the transformers that we have on our power lines. So possibly weeks, I wouldn't say several weeks, but I mean 1 to 2 weeks of bombardment where we wouldn't be sure if we want to turn the power grid back on, because remember, we probably had to shut off all the spacecraft and not communicate with them. So like a safe time period would be at least a week, possibly 2 weeks before we would turn things back on and be sure that we're pretty safe during a Carrington level event. And of course, there's always that other little concern is the Carrington event the maximum solar storm that the sun is able to release? We also don't know that. We have only been observing since around the 1850s or so, just shortly before that. So we don't have enough time sequence time series to know what it's capable of exactly.
So actually, we've only been observing the sun, its storms for a couple hundred years, but we do have histories stored in tree rings where we can study the effects of similar scale particle events. Yeah.
How often does it occur? Tree rings.
So it's always an issue, like trying to backtrack what happens in the atmosphere to what was actually happening on the sun. But a comparable scale event, vaguely weaker, maybe every 500 years or so.
Okay. So we got some time.
There was a question from back here.
Thank you. Hello. The question is for Robin. I would like to ask, how long does the dark matter last, or what's the lifespan, and what happens afterwards? And if I may, I have a second question for Gabe. What government, like DARPA, research, what's happening there in terms of sun flares? Like, is there a certain, how utility is going to protect what we have? Is there some cool research that's going on? Thank you.
I guess I would start. Yeah, that's a good question. I mean, the short answer is we don't know. We really know very little about dark matter. We probably know it's a particle, but we really only have evidence it interacts with other our normal particle like us through gravity. There is depending on different models, they might weakly interact with our matter with a very weak interaction, or they might not do anything. They might decay, they might not. I mean, we really do not know the detail, but we only we know they exist and they have mass and they they interact with astrogravity, but that's about it, like as a confirmative answer.
Okay, so I am more familiar, just because I did my PhD in the UK, with the UK's Met Office, which is their space weather monitoring organization. And essentially, if they were to detect a massive solar storm on the way, the plan is to let operationally the people that run the power stations begin a partial shutdown. In particular, the plan for the UK, at least, would not be to shut down the entire country because, perhaps there is no, perhaps they were wrong. Perhaps the scientists didn't really get it right, and it wasn't necessary to shut it down. But yeah, they would at least, I guess, kind of space it out so that part of the country would be disabled and the other part would not, allowing them to retain some functionality, like for the purposes of like military monitoring, because sometimes we have to worry about what happens during these blackout events. And also, things like hospitals and things like this, where if you shut off the power, people will die because they require devices that are plugged into the electrical grid to stay alive. So it's a big decision. And at least in the UK, it's pretty well formalized on how the process would work. They would essentially shut off part of the grid, letting part of the grid be damaged, potentially, and the part of the grid that's turned off would eventually be able to turn on again to start the factories up and start rebuilding transformers as quickly as possible. And in the case of the UK, they do have a large, I wouldn't call this reservoir, stockpile essentially of transformers and replacement electrical grid stuff in case this were to actually happen. I believe the US has a similar plan, but it is much more state level organized. In some states, California has a more cohesive plan than, let's say, let's just say some other states. But yeah, a lot of these big decisions are come down to solar physicists and understanding whether our detection techniques and whether our models and ideas of where these particles come from are correct, because these are really big decisions that could have military implications, as well as the implications that directly affect people's lives. Just shutting off the power, because probably there will be an announcement that goes out to our phones that says, "Hey, we're going to shut off the power." And then what? Who knows? So there's also sort of civil issues that can occur when communication just shuts down. So yeah, it's a big decision. Some countries have made better plans than others, and I expect if this were to actually occur, this wouldn't be the end of civilization. Just some places will be better off than others when it comes to recovery.
I just wanted to mention, I don't know if you're familiar with this, but there was a series in the UK that's aired on PBS here called Cobra, with Robert Carlyle as the Prime Minister. And the first season of this involves a solar flare striking Europe, and it imagines what happens. I think it's like six episodes or something like that.
No, I haven't seen that, but that's messes up my whole idea for Hollywood.
But so I just have a question about this, and that is, the Carrington event, it set these fires because it's inducing currents in long transmission lines.
Yeah.
So even if you shut off the power, you're still inducing a current that can overwhelm and blow fuses and blow breakers on these transformers that are connected to that.
Yeah.
So you have to go through and actually disconnect electronic circuits from the long transmission to induce currents, right?
That's what I was mentioning with. I'm sorry, it wasn't too clear about that. But yeah, they would physically separate portions of the grid in the UK.
Okay.
In the US, I believe that may already be the case on state levels, but within an individual state, I'm not quite sure how that interaction works.
Okay, I missed that. Sorry.
I think I didn't mention that. So,
okay.
Yeah.
One quick announcement. If you wanted to look at the telescopes and you haven't been out there, they're going to go for about 10 or so more minutes. So it's still okay. You guys just came from outside. It's you can still see the moon and Jupiter and such. Okay, cool. So if you want to check out the telescopes, bebop on out there right now. Otherwise, let's keep going with this. This is pretty exciting. So, and we'll keep going for another 15 or so minutes. I'm going to get this gentleman, and I'll get you in a second.
So I have two questions. Do you know anything about those GFCI things, like bathrooms? like those
the electrical outlets?
Yeah, the electric outlets.
Not really. Sorry. Yeah.
Well, like it resets the circuits when an electrical component touches water, so it doesn't break.
Okay. Yeah.
Do you think those are effective in preventing solar?
Oh no. The current. Yeah, that would be nice if they did. But no, the current that's induced affects very long lines of connection. So essentially, the longer your continuous wire, which is something that like the electrical grid is concerned with, as opposed to your house, where your the longest connection is maybe, I don't know, 100 feet, a wire in your house. That's not really long enough to start generating electrical current that would be a problem. So I think those small little plugs probably wouldn't do much. They would protect your devices specifically, but it's the grid itself, those power lines and stuff like that would be damaged. So that even if your phone and your computer were fine, you wouldn't be able to recharge them. Yeah.
And second question: have you guys ever heard of muon-catalyzed fusion?
Sorry?
No,
I'm not familiar with you.
Okay.
We're not doing that probably exists. I don't know, do you get
Sounds realistic.
Sounds like a real thing. Yeah. We know some stuff, but we're not plasma physicists, so we don't know that stuff as well. He had a question first, and then I'll get.
I had a question about coronal heating, but I could ask a dark matter follow-up if I could. For a while, I was starting to wonder if some of the extra gravitation was coming from the mass of all the papers that have been written about dark matter. Now that the James Webb Telescope is finding galaxies to redshift 15, a few 100 million years after the Big Bang, at what point, or at any point, can the degree of clumping start to constrain a little bit, either eliminate some of the proposed candidates or tune the degree of interaction that they have? At what point could that actually tell you some of the things that don't work?
Oh, I guess so. First is like the GWST results on like early. So they are finding like a lot of like the galaxy really early, kind of actually a lot more galaxies are expecting from theory. And I think in news, I sometimes see they claim like, there might be some new dark matter or something, but usually consensus is like, because like this is the first time you're actually having like a large enough sample of galaxy at so early. So there are like a lot of like the galaxy formation, star formation thing at such an early time we don't really understand. So I would mostly contribute them to our poor understanding of like a really, really early universe. Like 15 is like really, like maybe like it's way less than 100 million years, probably.
It's on the order. Redshift 15 is on the order of like 150 million years after the Big Bang, something like that. Not really. The best constraints we have on the temperature of the dark matter between being cold dark matter versus warm dark matter are more from being able to look in our nearby surroundings and finding smaller and smaller galaxies, and thus smaller and smaller clumps of dark matter that are surrounding those galaxies. Yeah, so that's our best constraint, is looking at the nearby stuff, because we can look really deeply, whereas the stuff in the early universe is so far away that it's very hard to look at the small stuff. We're only seeing the most massive galaxies and the most luminous galaxies at those great distances. But yeah, thus far, that is a constraint, and we're using that, and there are increasingly discovered with some of these all-sky surveys, the ability to find smaller and smaller galaxies where they're galactic halo mass, where like the Milky Way's halo mass is like 1 trillion times the mass of the sun. These are galaxies that are like even as down as far as 1 million or 10 million times. Yeah, that's right.
Yeah, but like, so just to add a little bit, it's like there are like constraints on dark matter, like in both like from astrophysics, cosmology, or like lots of dark matter experiments. We have good constraints, but like having constraint doesn't really tell, but they're like doesn't tell you what they are, right? It really tells you what they are not, which we have a good idea. Like we know they are not warm dark matter. We know like they can't have like a large interaction. You know, we do have quite a bit of model, but it just doesn't tell what it is, right? That's
Yeah, they're not rogue planets. They're not black holes. They're not neutrinos. They're not all sorts of things. Did you? Okay. There's a lot of things we know they aren't, but we don't yet know what they are. You want to add? Oh, there's so many questions. This gentleman was next, and then I'll get to you, and then I'll get to you.
I know this might or might not be your area of specialty, but if you could talk a little bit more about the Parker as a data collection instrument and a couple of different things. One of them was you mentioned that the heat shield was very resolute, very, very resilient. I was wondering what makes it different from other data collection situations in the past. And secondly, is it survivable in the case of, like, I guess you call it the Carrington event?
So the Carrington event released a lot of particles, but the sort of ambient temperature probably didn't rise much at all in between the sun and the Earth. It was just we were bombarded with these energized particles. So in the case of its heat shield, Parker's probably fine in that sort of case. The heat shield allows it to get much closer, and we're able to measure these energized particles before like other effects, which seem to affect everything as we move further out into the universe, called turbulence. There's I know a whole bunch of turbulence people who can explain everything in the universe, which is turbulence at different scales. So by getting closer to the sun, we're able to measure these particles and these ejected events before that turbulence effects really starts to change and distort what we're actually measuring farther out, let's say here at Earth with other spacecraft. As for whether Parker would survive a Carrington event, so like I said, the heat shield would probably work fine. But I believe I do know that we have what we call dynamic thresholding, which means our particle detector will turn off if it's bombarded by too many particles. I don't know about the other 3 instruments on the device. We have a few others, but yeah, they essentially all will be affected, and I'm not really sure. Personally, I have no idea what the limit of bombardment by energized particles are, but I'm sure the Carrington event is certainly capable of producing that, and probably Parker may survive thermally, but electronically, I wouldn't have my hopes up for that, especially if we're very, very close in. So yeah, I think it's built to survive the regular solar cycle, but a really, really extreme event, very far up close. Unfortunately, we're not constantly transmitting data. So if Parker was to burn up or, well, be destroyed in this sense, then yeah, unfortunately, we would lose that data because it only transmits when it gets far away from the sun, when the radio noise is a bit lower. So like right now, it's collecting data. We've had some really interesting strong flares and coronal mass ejections, but I won't actually be able to learn anything about them for probably another month and a half until it gets close enough where it can transmit data to the Earth. So that's unfortunately a problem. If we were to actually get the Carrington event, Parker probably wouldn't be able to tell us much about it. So yeah. Hopefully we don't get the Carrington event. Like, by the way, I'm not really looking forward.
Yeah, hopefully we don't. There was a quick question just from online before I jump back into our audience. How close are we to understanding the coronal heating problem and coming up with a solution? Like, is Parker going to reveal the answer on a few more passes, or?
No. I think Parker isn't really meant to answer the coronal heating problem.
Okay.
And I think this is I think at this point we should probably stop calling it a problem. Like the details
the
of coronal heating
situation.
Yeah, the coronal heating situation.
What's heating up the corona to this ridiculously high
So
temperature?
as I mentioned, it's a conversion essentially of magnetic energy into heat energy. That seems to be the key culprit, and we can figure out a good portion of the energy needed to raise the temperature for these particles up to a couple million degrees Celsius. So we understand that. It's the details of what maintains that temperature that's tricky. So when we get large flare events, of course, it makes sense. We see lots and lots of magnetic conversion to heat in this momentary period of time. But then, there are sometimes years where the sun hardly spits out any major flares or major coronal mass ejections, and it still remains around, on the low end, 1 million degrees in the low solar atmosphere, low corona. Why that's maintained will require different answers from different solar physicists, but essentially there's several people who think that there are small jets which are warmed very, very close to the surface, and that hot material is kind of spit upwards. There are others that think we have sort of what we call wave heating, so wave interaction passing through. We would call these alphenic waves, but that wave interaction basically would create heating, which maintains this minimum temperature of like 1 million degrees Celsius, and honestly a whole bunch of other theories for this. But if you combine all of these together, we're really trying to work out the details of not so much which one of these, but how much contribution from all of these different ideas actually leads us to a consistent minimum temperature of 1 million degrees, and why we occasionally get up to 10 million degrees or so. And the trick is it's really hard to tell what that high temperature is, because with most of the spacecraft that we have up now, using a variety of methods by combining different filters and stuff like this, we can kind of tell a maximum temperature up to about 10 million degrees Celsius. But beyond that, it gets a little tricky. You need things like my spectroscopy device to actually figure out the energy input above 10 million degrees. And so basically we'll have more data essentially, and we could use, I think somebody was talking about an AI device later on to really figure out the contribution from all of these different methods and different observations, and really sort out the details of coronal heating, as opposed to calling it a problem, because it's not. I mean, yeah, it was a problem 150 years ago, but I think
when the Carrington event occurred, it sounds like it was a real problem.
Yeah, it was a real problem. Yeah. So sorting out the details, I think, is a better way of phrasing it.
Okay, yeah, that's fair. Okay, there are some questions here. Do you still have a question? Yeah.
So my question is what's being an astrophysicist like?
What's it be? Oh, open-ended question.
In general, how are you able to live? Are you able to live comfortably?
Oh, are we able to live comfortably?
Yeah, and
well, I'd say
how's the job experience in general? How's the workplace like?
Okay. So occupationally, is it rewarding both financially as well as professionally to be an astrophysicist? What do you think, panelists? Are you happy with your chosen occupation?
This is being recorded? Is that right?
It's live streamed.
Oh boy.
I'm going to send it to your supervisor.
Has its ups and downs, but honestly, it's mostly ups. I'm very interested in the sun. I'm very interested in what goes on in the solar system. Things personally that I can interact with, and I think we will send astronauts here in my lifetime. I don't have to study the rest of the universe like you guys do. It's really cool stuff, but it's not for me. And that's really a big thing about being an astrophysicist, is I have a lot of freedom to kind of research and go into what I want. And thankfully they pay me to do this, to focus on the sun and stuff like that. And I'm really, really grateful on nearly a daily basis that people give me money for
But do they pay you well? Is the question.
Not nearly as much as I would like, but yeah, I have a decent living. That's not really a major concern when it comes to being super poor or anything like that. I'm just like medium poor or something, but yeah, I really, really enjoy the intellectual freedom, and I've I don't get this in my salary, but I get to travel all over the world a lot, which is a really nice perk. If you're doing simulations, maybe you don't get to travel around as much. So solar physicists get to travel around and chase things around. So this was a big benefit for me. But depending on your interests, you can always find some sort of path and some sort of area that really suits you, as long as you pursue it. So if you're up for the math and all the homework and hard work and surviving PhD and all that stuff, then I highly recommend it.
Speaking of salaries, as I like to complain about being on a grad student salary because it's pretty awful, but there are very few professions where you get paid to go to school, and I'm really grateful for that, honestly. Like, living wage is debatable, but I live comfortably and I get to do something that I find so extraordinary and fantastic. And like, I'm not personally doing any like life-saving work. Like some of the people who are involved in instrumentation, like their work gets to go on and like be used and utilized in day-to-day applications that have really meaningful impacts. But I just get paid to do a passion project basically. And there's not a lot of vocations where you can say that, I feel like.
The only thing that I'd add is, graduate students, postdocs, even research scientists don't usually make a lot of money in this field. But as was described by my colleagues, it's really a trade-off between what you're valuing in your life. Work, for the most part, it can be stressful like any job, but it's really exciting to be able to pursue, your interests in trying to understand how the universe works. And I think that's true of all scientists for the most part, but it may come at the hit of not being paid what you would be getting if you're writing, large language models at Google and being paid $1 million a year. So it's a trade-off. You don't get a lot of money, but you get freedom to pursue cool things and think a lot about cool topics that is kind of crazy that you get paid to think about these things. What's that? And occasionally you get a free beer at Doghouse if you run the astronomy on taps and give a presentation there. That's correct.
Yeah, I think it's a pretty accurate description, and maybe I will change my mind when I become close to finish my PhD. But this is my second year PhD, but right now it's just, I would say it's amazing. It's just all this opportunity to pursue every different thing, and as working more on theory, there's even more freedom to do there's even more freedom to work on what I actually want to work on. So I find it worth it for now, but maybe it will change soon. So yeah.
Well, you got time.
Yeah.
Okay. Great question. Thank you. How are we doing on time? Oh, we're running out of time. Go ahead.
I have a question about dark matter. So the James Webb Telescope is able to see really close to the Big Bang now, right? So is there a point where dark matter is not present, or there's less of it, or is there an exception where dark matter isn't present or isn't needed, I guess? Yeah.
Right. So so dark matter so basically, so for galaxy, right, once even way before galaxies form, dark matter is there. You're asking when does dark matter start to exist? I mean, that's a great question, but that will require to be much early. That would be, we're talking about seconds or several seconds after a Big Bang. So basically, at least right now, the theory says the conventional wisdom is basically dark matter exists maybe probably even way less than a second, but it's we're talking about seconds, we're not talking about years. I mean, yeah, but I mean, obviously the very beginning is, it's not very clear. I mean, a major hurdle is because you have something called cosmic microwave background. So which means anything for photon, you can't observe past that. So that's kind of the earliest thing you can observe is something called cosmic microwave background. But during that time, dark matter exists like way early. So basically, if you see GFST, like dark matter is there. They have been around for a long time.
Is dark matter, just to make sure the online audience can hear, you're asking if dark matter is actively being produced right now, and if is there becoming more dark matter now versus early on? Not that we understand, no. We think the energy density of the universe is kind of fixed, and so over time, you're not producing new mass, you're not producing new dark matter, you're expanding outward, and so the existing energy, the existing mass is becoming lower density as the universe expands to fill that. It's kind of like if you've got I'm struggling for a good analogy. Let's say you've got a balloon's not a good example. Yeah, I always like the muffin analogy. Yeah, let's say you've got your muffin. You've got your that's a weird thing to say. You've got your blueberry muffin that you put the dough into your oven, and it it starts to heat up, and the yeast causes it to expand. And so all your blueberries at early time are very densely packed together. But as the muffin gets heated up, it starts to expand, and the density, the density of these blueberries drops because there's more space for those blueberries, and there's the same number of blueberries over time. And it's the same thing as we understand in our universe. The universe is expanding, but you have the same amount of stuff inside of that, and so it's getting lower density over time. Sorry to invoke the blueberry muffin analogy. I know, I mean, yeah, exactly. Pie and Burger might still be open. Maybe you could get a blueberry muffin there. Does that help you? Kind of? Yeah. I mean, we do think there are places in the universe where there's maybe less dark matter than other places. In the regions of galaxies or clusters of galaxies that were invoked before, we think there's, in the same way that there's more baryonic matter, normal matter, there's also more dark matter in those regions, whereas the regions between those structures, known as like cosmic voids, have less both normal matter, like what we're made of, as well as dark matter. It's not uniformly distributed across the universe. But was there a time when dark matter didn't really exist? Probably only in the first few moments of the universe, when everything was just confusion because you had all of your forces blending together because it was such a hot, super dense miasma of stuff. Yes, you can do one more follow-up question, but then we need to finish up.
Do galaxies form because the dark matter is there, or does the dark matter cluster because the galaxies are there?
Chicken or the egg? Chicken or the egg? Does the dark matter form because the galaxy's there, or vice versa? We generally think that the dark matter, because it's so much more mass component of the universe, the dark matter is the thing that clusters first, and then the galaxies form in the center of those dark matter structures. So we think it's, which one's the chicken? We think it's the egg. We think the dark matter formed first into these clumps, and then the galaxies formed kind of inside of those.
I have a follow-up question. So I believe it's called like Dragonfly 44 or something like that. It's a galaxy that's like 99% dark matter and just has a few stars around it. Is that
the opposite way? It's the reverse.
Oh, wait.
No dark matter.
No dark. Okay, sorry, the other way. So how is that possible?
Well, that's a fine question. I'm on a nature paper from last year. PI was Jorge Marino at Pomona College, where we looked at a series of simulations, the fire simulations that follow the evolution of galaxies, and found a handful of these galaxies that don't seem to have a dark matter component to them. And the idea, I mean, if the simulation is reproducing reality, which we're not sure that it is, but well, that's the point, is these are observed. A couple of these systems, like Dragonfly blah, 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 from the Dragonfly survey, have found galaxies that appear to have no dark matter in them, because the rate at which they're rotating and such doesn't seem to invoke that there's some additional unseen mass component to them. And so the simulation tried to explain that. And the simulation basically showed that these systems are dwarf galaxy systems, so they're a lot less massive than, a few hundred times or 1,000 times less massive than our own Milky Way. And they did have dark matter, but their trajectory around another larger galaxy like our own Milky Way took them too close, and it brought them in and it stripped off that dark matter while leaving the normal matter, the stars and the gas and the normal baryonic matter there, because that stuff is in the center of these kind of clumps. So you can strip off the outer layers, kind of like an onion, and just leave behind the core, the pearl, the galaxy in the middle. I'm getting crazy with my analogies here. And you could leave that behind. And so some of these systems that were created in this simulation left behind these galaxies that had very little dark matter left to them. And so that's one proposed by our group method of producing these galaxies that lack any kind of dark matter. So, okay. Thank you guys for sticking around. Thank our speaker. Excellent presentation, Gabe. And our fine panelists for their time up here. Just a quick reminder, the Death Valley Dark Sky Festival is in a couple of weeks, starting 2 weeks from tonight. It's free, it's open to all. There will be lectures, some of the darkest skies in North America and telescopes, and it's super cool. We'll be there. Our next Astronomy on Tap is in a week and a half, February 26th. At the Doghouse, featuring some cool talks, and it'll be good. And then our next lecture like this is March 15th about the NASA SphereX mission by one of the principal investigators of the mission. And then there's going to be a solar eclipse. So do that too, and we'll catch you guys at some future event. Thanks for sticking around.